Very good morning. Welcome for the next lecture. So, cooling load design and estimation. So, this is a topic I will address in this video. What is cooling load? So, cooling load is the rate at which a sensible latent heat must be removed from the space to maintain design conditions in terms of temperature and humidity. So actually cooling load is the total heat removed from the space so that space is to be maintained at specified conditions which provides comfort for the people. So how much heat that is present in the space, if we are able to remove same amount of heat, then the space is maintained at required conditions in terms of temperature, in terms of humidity. So that is done by knowing the cooling load. For that, we need to remove heat from the space, right? Heat from the space. So another definition for cooling load is the total heat required to be removed from the space in order to bring it to the desired temperature. Desired temperature by using any air conditioning refrigeration equipment, it is referred as cooling load. What is the purpose? The main purpose of cooling load estimation is to know the capacity of air conditioner required or to identify size of the air conditioner required. This is the main motto. The major purpose of estimation of cooling load is to determine the capacity of air conditioner or to identify the size of the air conditioner required to maintain design conditions during the period of high temperature. Whenever the summer period occur, automatically we are having more temperatures inside the space, but people will feel very comfortable at design conditions like 24 degrees centigrade, 50% RH. These conditions of air can be achieved by removing the excess amount of heat which is present in the space. For that, we need to evaluate how much cooling load is there. So based on the cooling load value, you can suggest, so 1 ton AC is sufficient, 2 ton AC is sufficient. So capacity of any air conditioner determined based on heat load present in the space. That heat load estimation is very important. And once again, cooling load is nothing but the amount of heat removed from the space so that the space is maintained at design conditions. The purpose of cooling load is to know the size of the air conditioner required or to identify capacity of air conditioner required to get design conditions in the space. So regarding calculation of cooling load, there are two components with respect to cooling load estimation. One is called as a sensible heat load. One is called as sensible heat load, and the another one is called as latent heat load. So one is sensible heat load, and another one is called as latent heat load. Let me clarify what is sensible heat and what is latent heat. So whenever heat interaction occurs, if it causes change in temperature, that may be temperature increment or temperature decrement. If there is any change in temperature, whatever the heat addition or heat rejection process, if it causes change in temperature, then it is referred to be sensible heat. It is said to be sensible heat. If it is heat is added, then sensible heat is gaining occur. If heat is removed, it is called sensible heat is lost. But whenever some heat interaction process occurring that causes change in temperature, then it is said to be sensible heat addition process or sensible heat rejection process. Then the amount of heat involved during the sensible heat addition or sensible heat rejection process is evaluated as mcp delta. This is the known formula where m is called mass of the fluid and cp is called as mass of the substance, cp is called specific heat of the matter, and delta T is called as change in temperature, initial minus final. Whereas latent heat. So this is called as latent heat. So whenever the heat interaction occurs, if it causes phase change, that means liquid to vapor, vapor to liquid, liquid to solid, solid to liquid. So if it causes phase change at constant temperature, then whatever the heat addition occur, it is called as latent heat. And this latent heat is evaluated as m into L, where m is called mass of the substance and L is called as latent heat of that substance. So mass into latent heat. So these are the two things you need to evaluate. And if you want to evaluate total heat from the space, then total heat equal to sum of sensible heats plus latent heat. For example, burning any fuel in the room, then automatically it increases temperature. It is considered sensible heat, right? So doing exercise in the closed space, automatically human body will sweat. So yeah, addition of moisture into the air, it is called as water vapor. But if it is taking a human body, so temperature also releases because of body temperature is higher during activity time. If outside is lower temperature, so there will be small gain of temperature by the surrounding air from the human body. So it is called sensible heat. Because of physical activity, body also sweat. So sweat is absorbed by the surrounding air. So it is called as latent heat. So human body or occupants in the space will generate latent heat as well as sensible heat. For example, operating any electronic component like TV or computer or any light, it generates only heat energy. So whatever the heat that is displayed by these electrical appliances or mobiles or laptops, all these are comes under sensible heat only. Let us see what are the sources for sensible heat load and what are the sources for latent heat load. The important sources of sensible heat loads are given here. So this is solar radiation. Number one is solar radiation. So when the space is exposed to the open atmosphere through openings, through windows, through the transparent areas, so radiation is entering into the space. Not only openings of windows, doors, but also there will be partitions between the walls, small cracks through which solar radiation is entering into the space that increase the temperature. So this is one radiation. And occupants, so major source of heat generation is occupants. Since human body temperature is 37 degrees centigrade, where the space is to be maintained at 24 degrees centigrade, then majority of heat is liberated by the pupil. So sensibility is gained from the occupants. And heat flow due to the conduction through exterior walls, floors, ceilings, and these are because of temperature difference. So whenever temperature difference exists between the inside space and the outside, so because of conduction phenomena, heat is transferred from high temperature to low temperature through walls, floors, ceilings, etc. Then one more cause for the sensible heat load is infiltration. So if it is a AC room, then pupil will frequent open and closes because of movement of the pupil from inside space to the outside. So whenever door is open, automatically along the person, some amount of outside air is also entering into the space that causes increase in temperature because outside air is higher temperature when compared to the inside space. So infiltration is nothing but outside air is entering into the space because of pupil interaction with respect to the room by opening and closing of doors. So that is called infiltration. And heat gain to the space due to ventilation. So we provide number of doors and windows. Whenever for ventilation purpose, sometimes the windows are open. Because of that, the outside hot air is entering into the room that adds heat. So it is considered as sensible heat load. And we are using for brightness, we are using number of electrical lights. So all the lights consumes electrical energy and releases light or heat. So it adds sensible heat. And we are using number of electrical appliances, like we are using generators, then we are using TVs, refrigerators. So all the electrical appliances releases heat as a result of consumption of electricity. So these are the major sources for sensible heat in the space. Then we are having sources for latent heat load. Sources for the latent heat. What do you mean by latent heat load? Whenever heat interaction occurs, if it causes phase change from liquid to vapor, vapor to liquid, or solid to liquid, so liquid to solid, vice versa is possible. Then whatever the heat interaction occurs, it is called as latent heat. During the latent heat, the temperature remains constant. The important sources for the latent heat are: number one is heat gain due to moisture in the outside air entering by infiltration through opening of doors. Whenever door is open, the outside air is entering where outside air is hot, so it is adding sensible heat. At the same time, whenever outside air is entering into the inside space because of opening of doors, so outside air contains more humidity, so it adds water vapor. So it is one of the source. Then occupants is another source. So occupants will cause sensible heat addition as well as latent heat addition. So occupants generally do any activity, as a result, sweat will be generated and sweat is absorbed by the space. So heat gain due to condensation of moisture from the occupants. And in the space, if there is any cooking process occurring, automatically steam will be generated. That steam is added to the space so that air is humid. So addition of any water vapor content in the space, it is considered as latent heat. Not only these regions, then latent heat gain from products, materials brought into the conditioned space. So these are the major sources of latent heat. Once we evaluate all the sources that are comes under sensible heat and comes under latent heat, then total heat expected from the room is evaluated as sum of sensible heats plus sum of latent heat. So total heat removed from the space is nothing but cooling load of the room, that is evaluated as algebraic sum of sensible heat loads and sum of latent heat loads. So if you measure the sensible heat and latent heat of the space, it is nothing but total heat of the space. Based on that, we can evaluate and estimate the size of the air condition required for that room. Before moving to the cooling load calculations, we must know one parameter called room sensible heat factor. So what is room sensible heat factor means? It is the ratio of room sensible heat by room total heat. Just now, I already told how to calculate sensible heat and latent heat. Once you know the sensible heat and latent heat for the room, then you must calculate room sensible heat factor. What do you mean by room sensible factor? It is the ratio of room sensible heat by room total heat. What is room total heat? The total heat is nothing but sum of sensible heat and latent heat. If the space is considered for a room, then it is considered room sensible heat. So room sensible heat factor is the ratio of room sensible heat by room total heat, where room total heat is room sensible heat plus room latent heat. So this is way you need to evaluate room sensible heat factor, which is mostly used for used in cooling load estimation. So look at psychrometric chart. So y-axis indicates the specific humidity and x-axis indicates dipole temperature, and this is called as the saturation curve. And S is called as supply condition of air from the air conditioning unit, and R is called as design condition of the room. Right? R is called as design conditions of the room. S is called supply condition of air. If you join S and R, whatever the line is formed, it is called as room sensible heat factor line. So whatever the line is formed, it is called as room sensible heat factor line. So the line joining S and R is known as room sensible heat factor line. And if we extend this RS line towards saturation curve intersection point, it is called as ADP, which stands for apparatus dew point. It stands for apparatus dew point. And if you draw a vertical line from point R and draw a horizontal line from point S, so intersection point we will get, then the lines which we will draw from point R, point S, and the intersection point. So the intersection point to point S, it is called as RSH, and the above one is called as room latent heat. Room latent heat given by the R to this point, and room sensible heat because of change in temperature TD1 to TD2, it is shown by the S point to this point, it is represented as RSH. At the same temperature, there will be change in water vapor content. From this point to this point, it change in omega or water vapor content. So it is shown RLH. So if you know room sensible heat and room latent heat put together, it is called as room total heat. If you know the conditions of supply and if you know the design conditions, locate the points as S and R. And if we join, automatically we will get room sensible heat factor line. If we extend, we will get a point called as ADP, operator's dew point. What do you mean by operator's dew point? It is the temperature of the cooling coil Whenever the air is in contact with the cooling coil surface, it is immediately converted into dew. That is called as apparatus dew point temperature. Right? Is it clear? Now I will introduce some terminology like GRSHF, ERSHF. So in the earlier slide, I already explained room sensible heat factor. So what do you mean by room sensible heat factor? It is the ratio of room sensible heat by room total heat. So what do you mean by room total heat? Room sensible heat plus room latent heat. So you need to add all the heats related to sensible heat, then it is called room sensible heat. Similarly, sum of all latent heats, it is called room latent heat. So if we sum up room sensible heat and room latent heat, we will get room total heat. Then grand room sensible heat factor. So what do you mean by grand room sensible heat factor? If you consider the infiltration load, then it is called a grand room sensible heat factor. So room sensible heat factor, we neglect the infiltration load. What do you mean by infiltration load? Whenever the door is open, outside air is entering into the room, that increases sensible heat as well as latent heat. If you consider, then the room sensible heat factor becomes grand room sensible heat factor. So grand room sensible heat factor is grand room sensible heat by grand room total heat. What is grand room total heat? Grand room sensible heat plus grand room latent heat. What is grand room sensible heat? Room sensible heat plus, because of whatever the heat is added due to infiltration, that is considered as outside air sensible heat. If you want to calculate grand room latent heat plus outside air latent heat. So we need to consider how much heat added because of infiltration, that is outside air sensible heat to the room sensible heat, that gives grand room sensible heat. Similarly, room latent heat plus how much heat that is added as latent heat due to infiltration, outside air latent heat. Both are evaluated here. If you consider outside air sensible heat, it is evaluated as 0.02044 V1. V1 is volume and multiplied by change in temperature. T1 is outside temperature of air, T2 is inside temperature. So we will calculate outside air sensible heat. Similarly, outside air latent heat is calculated as 50 V1 omega 1 minus omega 2, where omega 1 omega 2 are called as humidity ratio of outside air minus humidity ratio of inside air. So by using these relations, we can evaluate the infill. So volume of air and entered, it is called as V1, and difference in temperature gives the sensible heat. Difference in omega gives the latent heat. One more term called as effective room sensible heat factor. Effective room sensible heat factor. So when it is called effective room sensible heat factor means if we consider the bypass factor. So effective room sensible heat factor is given as effective room sensible heat by effective room total heat. What is effective room total heat? The sum of effective room sensible heat plus effective room latent heat. This effective room sensible heat is calculated as room sensible heat plus outside air sensible heat multiplied by bypass factor. Effective room latent heat equal to room latent heat plus 50 V1 omega 1 minus omega 2, that is outside air latent heat multiplied by bypass factor. When you taken into consideration of bypass factor, it is called as effective room sensible heat factor. When you consider only infiltration load, it is called a grand room sensible heat factor. If both are neglected, it is called as room sensible heat factor. Okay. And while solving any kind of problem related to air conditioning system, we need to follow some procedure, some terminology. Look at here. Point 1 indicates the outdoor conditions of air. Outside atmospheric condition of air is represented as point 1, right? Then number 2 indicates the design conditions of air. What are the conditions of air required in the space? That's why these are called as indoor conditions. Whereas atmospheric outside air, those are called outdoor conditions. So one is outdoor condition, so that indicates atmospheric air conditions. Then design conditions are indoor conditions represented as 2. Then 3 represents mixing condition. So at what point the reused air and fresh air is mixing. So mixing condition entering into the cooling coil. Number 4 indicates supply condition of air from the cooling coil. At what point the chilled air, conditioned air is leaving the cooling coil. It is called as 4. And we are using 5, but it does not give any sense, right? So we are using 5, but line 4 5 is called as room sensible heat factor line. Line 4 5 is known as room sensible heat factor line. And we are using another point called 6, which is stands for ADP, dew point temperature. So ADP stands for operator's dew point. ADP stands for operator's dew point. So we are using 1 to 6. In addition to that, there are 2 points called as A and B. A is called as the value obtained from the sensible heat factor value. So you are having a formula sensible heat factor equal to sensible heat by total heat. Whatever the value obtained, it is assigned as A in the psychrometric chart. And B is called as base circle or alignment circle. On the psychrometric chart, base circle is represented at 25 degrees centigrade, 50% RH. So remember this value. Base circle is identified at 25 degrees centigrade and 50% RH. Then line 25 is called as room sensible heat factor line. Line 36, it is called a grand room sensible heat factor line. Line 26 is called as effective room sensible heat factor line. I will show you with the help of psychrometric chart in the next slide. Just now I told all those things. Just it is theory description. Now look at here. So one is called as outdoor conditions. Just now I explained. So one is called as outdoor conditions, and two is called as the room design conditions. And point 3, it is called mixing condition of entering the cooling coil. So mixing conditions. Then point 4 is called as condition of air leaving the cooling coil. And if you know the supply condition or design condition, and we know the supply condition of air, then this line 245, it is called as room sensible heat factor line. This is called as room sensible heat factor line. And when you identify the mixing condition of entering the cooling coil, and you know the supply conditions, then you need to join 3 4, and if we extend, we will get ADP, that is operator's dew point. So grand room sensible heat factor, then we are having effective room sensible heat factor already addressed in the previous slide. So in this psychrometric chart, we need to locate point 1 based on given conditions. So 1 as outdoor conditions, 2 as design conditions. These values are given. So based on the given values of dry bulb temperature or relative humidity or wet bulb temperature, you need to locate 1 and 2. Then mixing conditions given. So you need to identify whether mixing taking place before cooling coil or after cooling coil. That is also very important consideration. So while solving problems, I will address. I will concentrate more emphasize on how to locate 3. So 4 is called as supply condition of air. In any given problems, whether 4 or 6 is given, then immediately you need to join 3 to 4 and extend, we will get 6, or 6 is given, 3 is known, so you need to join 3 6, automatically it will intersect the line 4 5. So that point is called as supply line 2 5, which is referred as room sensible heat factor line. So we will get 0.4. So these things are already given. So infiltration, we need to consider outside air. These are also already addressed in the previous slide, right? So this is the plot. Go back. Right. Okay. So as per the given problem, in the given problem, we need to locate 1 as per the given data as outdoor conditions. 1 is called outdoor conditions. You need to locate here. Then 2 also given. So outdoor conditions are given in the problem. Indoor conditions are given in the problem. Locate 1 and 2. That is first step, right? Then evaluate A. A is called a sensible heat factor. How do you evaluate sensible heat factor? It is the ratio of sensible heat by total heat. So total heat means sensible heat plus latent heat. Based on the given heat loads in the space, we need to evaluate sensible heat factor. For example, 0.7. So at point, this is called sensible heat factor scale. At 0.7, you need to locate a point, that is A. right? And in the psychrometric chart, there is a small circle given which is 25 degrees centigrade, 50% RH. That is called base circle. So identify B. Then immediately join AB by using scale unit to join AB, right? Then join, already we located 1 and 2. We located 1 and 2 earlier, then join AB. With respect to line AB, from point to generate a line which is parallel to the line AB. I'm repeating again. So first you need to evaluate sensible heat factor, and the value is assigned as A. And this is called sensible heat factor scale from 0 to 1. For example, if it is 0.8, at 0.8 locate a small dot and it is assigned as A. And at 25 degrees and 50% RH, we are having a small circle in the cyclometric chart itself. That is B. Then join AB. Join AB. So this line is called as baseline or alignment line or reference line. And after locating this AB points and joining AB, so we need to locate 1 and 2. Then from point 2, you need to draw a line which is parallel to the line AB towards saturation curve. Wherever it is intersecting the point saturation curve, that is called as 5. This is called as 5, right? So line 25 is called as room sensible heat factor line. Room sensible heat factor line. Then mixing condition is given in the problem. Based on the given information, we need to identify 0.3. So 60% reused air, 40% fresh air, or 60% fresh air, 40% reused air. Based on those conditions, we can identify 3. Once you locate 3, then automatically the ADP or supply condition of air is given. So based on the given information, whether 4 is given, for example, supply condition of air is leaving at 15 degrees centigrade. So at 15 dry bulb temperature, dry vertical line, automatically line 25 will be intersected. Intersection point is 4. Once you know the 4 and 3, join 3, 4 and extend towards saturation curve. Intersection point is 6. That is called as ADP. ADP stands for operator's dew point, right? This is the way you need to get 1, 2, 3, 4, 5, 6 points. 1, 2, 3, 4, 5, 6 points. The line joining 3, 4, 6 is called as grand room sensible heat factor line. The line 2, 4, 5 is called room sensible heat factor line. If you join ADP and 2, it is called as effective room sensible heat factor line. It is known as effective room sensible heat factor line. With respect to line 1 to from point 4, need to draw a line in such a way that we will get 4 dash. We will get 4 dash. Then from 6 to 4 dash, it is called as bypass factor. It is called as bypass factor. Then 4 dash to 2, it is called as 1 minus bypass factor. Similarly, from 3 to 4, it is called as 1 minus bypass factor. From 6 to 4, it is called as bypass factor. It is called as bypass factor. So we are having 6 to 2 is called effective room sensible heat factor line. 2, 4, 5 is called room sensible heat factor line, and 3, 4, 6 is called as grand room sensible heat factor line. Right?